Local, maxima, and minima. What do derivatives tell us about a function and its graph? Derivatives show where the functions are increasing and or decreasing concavity and patterns. So we're going to our calculator and we're going to graph the following function. We're going to put this in y equals. So in your calculator or on your calculator, press y equals and you should see the y's happen there. And you're going to plug in x cubed, x raised to the third power, minus 12x plus 1. And I really do not know what window I am on right now, so I'm going to make sure we all have the same window. Press zoom and 6 for the standard window, and we'll see what we can see. That ensures that we're viewing in the same friendly window. So we are sketching and labeling the graph. Can we see all of the x-intercepts, the y-intercepts, the maximum point, the minimum point? I don't think we can, so if we can't, we need to change the window. So my graph looks kind of funny, so I'm going to check to make sure everything's in the right place, and I see it is not. So x raised to the third power, come out of the exponent, minus 12x plus 1, and we should see a different graph appear. I'm already in Zoom Standard, so I'm going to press Enter, or Graph. Let's go to the window, and let's change our window, negative 8 to 8, or the x's, and the y's will be from negative 25 to negative 25. And press Graph. Now if you get an error message saying a syntax, then that means you put the wrong minus sign. You need to use this one. So what I did in the notes is I found all of the points of intersection. I found the maximum point, the minimum point. I can see them, and because this graph continues, these points, the maximum and minimum points, are critical points, and we're going to find that using the first derivative. So use the first derivative, factor it, and we find the parts, set the parts equal to 0, and we find the critical points. Now once we find the critical points, we can determine if we have a maximum or a minimum based on what is happening with the slope of the graph. So if I plug in negative 2, or not negative 2, but some value to the left of negative 2, let's say negative 3, and I'm going to plug that negative 3 into the derivative function and just determine whether it's positive or negative. X plus 2, is that negative when I put the x as negative 3? That is negative. Negative 3 minus 2 is negative. A negative times a negative makes a positive, and our graph is continuing upward. From negative 2 to 2, we'll use 0. And when I plug 0 in here, I get a positive, and when I plug 0 in there, I get a negative. So a positive times a negative is a negative, and our graph is sloping downward. And from negative or positive 2, we are going to put some value to the right of 2, and let's put 3. And if I plug 3 plus 2 is 5, that's positive. 3 minus 2 is 1, that's positive. So a positive times a positive is a positive. Now notice the 3 does not change, so I don't have to worry about plugging a number in that. Find the zeros of the original graph by letting y2 equal 0. And we find the intersection points, and here are the intersection points, and I'll show you how to do that. Y is equal to 0. And you already know how to find the intersection points, but I'll show you one. So we press second, trace, number 5. We get close to the point we want to intersect. If you jump to the red line, that is a linear function, so you can move along it quicker. So I'm going to choose get close to this first point, press enter, 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 and that gives me my point, which I have labeled here as 3.0504, comma 0. This negative 2e negative 12, that's 0. Okay, so the critical points are where the original graph changes direction, where the slope at that point is 0. So right here, if I draw a horizontal line through that, or a tangent line, it will be horizontal, and that negative 2 is where this graph, the first derivative graph, crosses the x-axis. This critical point at 2 is where it's going to cross there as well. So we want to plug those values in. We go to our original function, and we want to press trace and negative 2, and that should give us the point 17. The y value is 17, so the ordered pair is negative 2, 17. What is the minimum point? We know that the value is 2, so we press trace and 2, and it is 15, negative 15. To find the derivative of the second derivative, we use that to determine concavity. So the second derivative of 3x squared minus 12 is 6x. Set that equal to 0, and that is when x is 0. So if I plug in any value to the left of 0, let's say negative 1, then negative 1 times 6 is negative, and we have our graph is the slope of our graph, our derivative function is negative. And if I use some value to the right of 0, let's say 1, 6 times 1 is positive, so our slopes are positive. So at 0, concavity changes from concave down to concave up. So here's concave down, we get to a point at 0, and then it becomes concave up. When concavity changes, we have an inflection point. So at 0, so I press trace and 0, that is where concavity changes. So at 0, 1, concavity changes. At 0, 1, the critical point of the second derivative, concavity changes from concave down to concave up. And we'll go through these, the summary here. Suppose P is a critical point on a continuous function, reading the graph from left to right. If the function f prime changes from negative to positive at point P, then there exists a local minimum at point P. If the function f prime of x changes from positive to negative, there exists a local maximum or minimum. And the reason it is local is because this is a local maximum, because there are many other maximum values greater than negative 217. So I see right here there's a point at 20. And same is true for the minimum. These values over here are less than this minimum, so it's called a local maximum or minimum. So on page 81, how many critical points do you see? 1, 2, 3. 2 local maximums and 1 minimum. During an illness, a person ran a fever. His temperature rose steadily for 18 hours. Steadily means the slope is the same, constant slope for 18 hours. When was there a critical point for his temperature as a function of time? At 18, it said it went down steadily for 20 hours. Here's number 20. We have x to the fourth minus 4x cubed plus 8x. The critical point is at x is equal to 1. So we're going to use the second derivative test to define concavity and identify it as a local maximum or a local minimum. So if I plug in, I've taken the first derivative, now this is the second derivative and I factored it, so my critical points are 0 and 2. What's happening there? So at -1, I plug in, I get a negative and a negative, that's a positive. If I use 1, then 12 times 1 is positive, 1 minus 2 is negative, a positive times a negative is negative, so we have the second derivative is negative when x is equal to 1, the graph is concave down. So there exists a local maximum at x is equal to 1. Okay, so for what values does f have a local maximum or minimum? Well, let's look at the graph of the derivative. So the critical points are where the graph crosses the x-axis. We see that the graph crosses x at 1, 3, and 5. The derivative function, this is positive and this is negative, at 1, at x is 1, there is a maximum. This is positive, and then it goes to negative, so there's a local maximum there, because the derivative is positive and then changes to negative. At x is 3, we have a local minimum because this derivative is negative and then changes to positive. But at 5, when x is 5, the derivative has no sign change, so a local maximum or minimum exists there.